So my name is Ola Kalinowska, and I am a PhD student at Northwestern University in the Center for Robotics and Biosystems. And today I'll be presenting work that was done in collaboration with a number of researchers at DeepMind during my internship there earlier this year. So I want to start by posing that communication is really what enables effective cooperation, and we see evidence of this across different types of teams. We see it in human-human teams, we see it in hybrid teams of humans and machines, and we see it in teams of autonomous agents. And by studying the process of communication emergence, we can better understand how communication emerges between people, and we can design machines that can cooperate both with people and with each other. And I really want to emphasize the emergence part of communication emergence, particularly because there has recently been a lot of progress on developing large language models that are able to communicate using natural language by being trained on large data sets of human dialogue. And while this is interesting for some applications, there are some applications where we might want to enable nonverbal communication, and there we often don't have access to such large data sets, and so understanding how communication can emerge is beneficial. And one such application that I'm particularly interested in are nonverbal interfaces for robotics. So as assistive devices are becoming more and more capable, we are increasingly limited by how we communicate with them. So they could be providing significant assistance. And for instance, if you take the example of a powered prosthetic hand that could help with daily tasks, the user lacks feedback on what the autonomy is doing. And they could receive feedback, for instance, through a haptic sleeve on their upper arm, as illustrated here, for instance, through different patterns of vibrotactile sensations. This could help the user anticipate what the autonomy is about to do and, for instance, provide corrective movements in anticipation of that. But we don't have an intuitive haptic language that we could readily apply in this situation. And so having a way to algorithmically facilitate communication to emerge would be helpful. And so we can study communication emergence using artificial agents. And this is what we do in our research here, where we model the agents as neural networks and we enable them to learn through reinforcement learning. So we have a speaker and a listener that can generate either messages or environmental actions that affect the state of the environment and also the observation of the other agent. And that enables the agents to cooperate to achieve a common task. Once they achieve the task, they receive a reward, and that updates the weights of the neural networks. And so there's a number of studies that investigate how communication emerges in reinforcement learning. And many of the existing work studies emergence of communication through cheap talk in one-step referential games, also known as the Lewis signaling task. And so many of you might be familiar with the task, but I'll just briefly recap it here. In this task, we again have a speaker and a listener. The speaker has access to an object or an image from a set of 100 or 1,000 different images. Based on that image, they generate a message which gets broadcasted to the listener, who, upon receiving the message, selects an image from a set of 3 to 5 images, often referred to as distractors. If they select the same image that the speaker had in mind, both agents get rewarded and the episode resets. And so in this setup, we refer to the communication as cheap talk because it's guaranteed and free to the agents. So the agents aren't reasoning about whether to communicate, they're only reasoning about what to communicate. The speaker sends a message at every time step, and it's always received by the listener. And in this setup, it's well studied. So we observed that it can lead to successful communication emergence, both in people and in artificial agents. However, it has some limitations. For one, the emergence of communication is relatively slow. Here you see a convergence plot from one of our experiments, and it shows that it takes 3,000 to 5,000 episodes for agents to agree on a successful communication protocol, and that's representative of literature. The communication protocols are often inefficient, so the speaker tends to flood the communication channel and fill it to capacity, irrespective of whether they are conveying proportionally or conveying information that's proportional to the complexity of the task. And lastly, the communication is often non-generalizable. So here you see a figure from a prior study where the agents were trained again using the Lewis signaling task on the photographs in the top row, and then they were evaluated both on the photographs and on white noise. And it turns out that agents were almost as good at differentiating white noise as they were at communicating about the photographs. And so that suggests that they were communicating about non-generalizable pixel values rather than salient elements of the images that could generalize to other tasks. And so our hypothesis going into this experiment was that time is a key pressure in communication emergence, and it's not captured when we study emergence using cheap talk in these one-step referential games. But if we did capture the concept of time somehow, then that could lead to faster learning and the communication would be more concise and more efficient. And so as our test bed, we design a multi-step task in a grid world environment. Again, we have a speaker and a listener. The speaker has access to privileged information, so they can see the layout of the maze, the location of the listener, and the location of the goal, while the listener can only see the 3 pixels that are right in front of them, but they can navigate the maze towards the target. The targets are randomly located in one of the 4 corners of the maze, and if the listener successfully reaches one of the targets, both agents get rewarded, so they're incentivized to cooperate. And so we first wanted to validate that communication is actually necessary to solve this task, and that agents, the way we've designed them, are able to find successful solutions to the task. And we, in fact, were able to confirm both of those statements. So here you're looking at learning curves from our experiments. In the top row, I am showing a metric of success. So when it reaches 1, that means that agents are on average finding the target in every episode. And so we see that with communication, they're on average succeeding at the task, with communication only partially. And then in the bottom plot, I'm plotting a metric of optimality. So this metric, when it's equal to 1, means that the agents are able to solve the task in the minimal amount of steps. So they're taking the shortest path to target, which usually suggests that they've found an efficient communication protocol. And again, we see that the agents that rely on communication can find optimal solutions, but without communication, that's not possible. And then we want to analyze a bit more in depth of what the communication protocol looks like and how the agents are communicating. So what we find is that they're using this just-in-time communication protocol, as we call it. And what that means is that there's a one-to-one mapping between the speaker's message in the current time step with the listener's action. So this makes sense because when the agents don't have memory, they're only relying on their current observation. And so we're plotting the communication protocol in the heat map on the right. And what's important here is that there is very little ambiguity in the interpretation of the symbols. So if you look at the y-axis, which is the speaker's messages, dependent on the environmental context. So for instance, the message 0 at a quarter is always interpreted by the listener as an up action. So the listener always goes forward. Now we modify the agents and we add memory. So we add a recurrent layer to the neural network. And we observe that the communication protocol changes slightly. So now the agents are using kind of a look-ahead communication protocol. What that means is that the speaker will broadcast the same message for the first few time steps of an episode until the first junction, and then they'll switch to a different message and consistently broadcast that until the next junction. So there's this repetition of the message and an anticipatory communication protocol. And we don't test this as much, but this could be a way to compensate for imperfect memory, and it could also add robustness to noise. So for instance, if messages become corrupt, using this type of look-ahead communication protocol, agents could be more robust to noise. So these were our preliminary analyses. We wanted to observe how the agents are learning to communicate in our task. And now we run two different experiments. The first one is a comparison between upfront and multi-step communication. And this is our way of testing this time hypothesis that I mentioned at the beginning. So far, the speaker was able to send a message at every time step, and the listener was able to take an action in response to that message. But because this is a relatively simple task, we can imagine that the speaker could send one upfront message at the beginning to encode the address of the goal location, for instance, top left, bottom right. And then the listener agent, when they have memory, they could reconstruct the path just based on that one initial message. And so we test this hypothesis, and this is a somewhat busy slide, but I'll walk you through it. Overall, we find that multi-step communication improves communication emergence. It makes communication easier to emerge and helps with the speed of emergence. And so in these plots, we're again looking at learning curves. In the top plot, you have the metric of success. So we see that both agents using multi-step and upfront communication are successfully reaching the target on average in every episode. But when we look at the metric of optimality, we see that the multi-step communication leads to much more optimal solutions. The agents using upfront communication converge much slower to optimal solutions. And then when we look at the communication protocols, what we find is that the upfront communicating agents have a hard time coming up with an unambiguous mapping of messages to target locations. So they often end up with protocols that are ambiguous. For instance, the message 3 in this top heat map might be sent by the speaker when the target is located in the bottom left or the top left. And so that means that the listener agent knows to turn left at the first junction, but it's ambiguous to them whether to go up or down at the second junction. And so overall, this seems like there's benefits to this real-time interaction where the speaker gets to observe the listener's immediate reaction to their message during multi-step communication. So then we run a second set of experiments, and now we want to find an alternative to cheap talk. So I described cheap talk as this guaranteed free communication that agents use in many of the existing tasks. But as an alternative, we explore situated communication, where the listener has an augmented action space. They can now either take physical actions in the environment, like left, right, up, down, or they can choose to stay in place, forego an environmental action that can bring them closer to the goal, and ask the speaker for information, so solicit input. And so importantly, the listener can take both communicative and non-communicative actions, and so they're reasoning about whether to communicate at all rather than just about what to communicate. And because of that, they're experiencing an opportunity cost to communication. Communication is no longer free because, like I said, they have to forego an environmental action to solicit information. And overall, we find that this communication paradigm also leads to successful communication emergence. I'll walk you through an example episode here. So on the left, you're again seeing the maze. The listener is indicated with green with its point of range of view. And then the target is located in the bottom right with a blue, indicated with a blue square. And here we see an episode rollout, and we see that the listener takes autonomous actions for the first few steps, and then at step 3, they choose to stay in place to solicit information at the junction. And upon receiving a message, they correctly turn right until they reach the second junction, where they again choose to stay in place to solicit information from the speaker. And again, they correctly turn right to reach the target. And we see this behavior across different types of agents with and without memory. I won't show you more results here, but we include them in the paper. And so overall, we find that our experiments support this idea that time is a key pressure in communication emergence, and that it helps shape the emerged communication protocol. And so there might be benefit from moving from one-step cheap talk towards multi-step situated communication, where at least partially we capture the temporal constraints of a real-world environment. And we observe that in general, that leads to faster learning, and the communication protocols are task relevant and more concise than using one step or using this guaranteed mode of communication. And in some of my ongoing work, I'm actually looking at how to apply these types of mechanisms like situated communication to improve the usability of assistive devices that I mentioned at the beginning. So for example, we can imagine using situated communication to selectively query the user for information when we model the powered wheelchair as an artificial agent. And that way, instead of constantly requiring input from the user, we can agree on a communicative convention where the user is only selectively querying the person for input when they have low confidence in what to do and when they're at a decision point in navigating the environment. And so if you have interest in that, I would be happy to continue the conversation. And if not, I'll end with that and take any questions.
Yeah, so sorry. So yeah, thanks for a great talk. If there's any questions here, please come forward to the microphone. Otherwise, maybe there are some questions in the chat as well. I see a notification, but if someone can see if there's questions there. Otherwise, I have a very superficial question, maybe. So when these speakers decide to talk, is that based on their observation of the entire grid world?
Yes. Yeah. So they decide to talk based on the location of the listener and the observation of the grid world, and also the location of the target. So the speaker is kind of like an oracle that has access to all of the information in this simulated environment.
And then this, so if a speaker gives some advice, is that just concatenated to the state that a listener observes, or how does the actual message, how is that represented for the listener for the action in the action space or state space?
Yeah, so it is concatenated. The listener does not have access to the whole map of the environment, so they can only see what's right in front of them. So the observation of the listener is its partial view of the environment, so just that those 3 pixels right in front of the listener, and then that gets concatenated with the message from the speaker.
Cool, great. Any questions in the room here? Online? All right, well, then I think that I'd like to thank you for your talk, and we're moving on to the next speaker.